Hello there. Today we're going to be talking about the adiabatic reversible expansion of an ideal gas. It sounds a little complicated, so we're going to break it down in three parts. First, we're going to want to arrive at the basic equation of statics, and we're going to do that by looking at the differential volume of a liquid. So we're going to say we have a liquid here, and we want to take just a cube of that liquid. So I'm going to go ahead and draw out that cube. Alright, so we've got that cube. And so what we want to do is go ahead and give this cube some substance. So we want to say that this cube has a height. We're going to call that height. It's a change in height. We've got the change in height. And we want to mark this point as z. So this whole plane here is z. And so we want to see how this cube of liquid changes from point z to this plane dz plus z, right? Because we want to look at it, how it changes from these 2 points. And so each of these planes is just the area here. And so since we have this liquid, and we want to go ahead and apply force balance to it, so we're just going to go ahead and use a very common equation here. The force is equal to the mass times the area, or acceleration, sorry. So let's look at the forces. So in this equation, we're looking at just a section of this liquid. So it's a liquid, and we're going to say that this liquid isn't moving. So this is staying still. So this A is equal to 0, which makes this right side equal to 0. So what we can do is we can look at the sum of forces acting on this cube of the liquid we have here. So let's go ahead and just draw in the forces we have. So we've got a force of this liquid here acting on the top at this point here, and this force acting here is just a pressure, and so and the force we have acting here is a liquid. So the force we have acting here is the pressure, and it's a pressure because so the force we have acting here is a pressure, and it's the pressure at dz plus z, and this pressure is acting over the area here. And we also have a force of the liquid acting on the bottom of this cube, and that's just the pressure at z times the area. And then we also need to recognize that we have gravity occurring in this. So we've got a mass times the gravity, and I like to have gravity acting down, so we're going to go ahead and call this the positive z direction. And so we can go ahead and apply our force balance to this equation, to this situation, sorry, make an equation. So what do we have? We have the pressure at z times the area, and that's acting up, so it's positive, but we've got the pressure at the top times the area, and that's acting down. And then we also have the gravity acting down, and this is equal to 0. And I'm just going to write the sum of forces here. And so what we can do is go ahead and start manipulating this equation. So first thing we're going to do is pull out a negative A out of this. So then we get the pressure times dz plus z. So the pressure at the top, and then we've got that minus the pressure at the bottom. And then I'm going to go ahead and move the mg to the other side just to make it positive. And so now we want to recognize that we can take this mass, and because we are acting at an ideal gas, we know that the mass is equal to the density times volume. And so we also know that volume is equal to the area times the position, right? We know the volume from here. This is a volume, and we've got the area times the position, and that's the volume. So we can go ahead and plug in rho times our volume here. So we're going to make this mass, copy over this part of the equation. So we know that this is rho A dz times g. And I am going to go ahead and recognize that we've got an A, the area, on both sides, so we can just go ahead and cancel that. And so if we go and further simplify, we recognize that we are eventually going to try and solve, we want the change in position, all of these terms on one side, so we're going to just go ahead and divide that over. And at the same time, we're going to want to move the negative over to the other side just to simplify. So let's go ahead and do that. Alright, divided by change in position. Oops, that was weird. And we've got the negative rho, that's a rho, times the gravity. Alright, so a couple things we need to notice here. We need to notice that because we have the density and we're at an ideal gas, we've got that the density is equal to the mass over the volume. And at an ideal gas, we know that the mass is equal to the number of moles times the molecular weight. And we know that this is equal to the pressure times the gas constant times the temperature, because that's an ideal gas. And so that we know that rho is equal to the pressure times the molecular weight over the gas constant times the temperature. And so we can go ahead and plug this in. But before we do that, we also need to notice that this here is just a change in pressure over this position from z to dz plus z. So that's really just a change in pressure. So we can just go ahead and call this, we're going to go ahead and call that dp. So if we go ahead and rewrite all of this, we end up with dp over dz, and make that equal to the negative pressure times the molecular weight over the gas constant times the temperature times g. And there we have the basic equation of statics. Alright, for step 2, we're going to be talking about the first law of thermodynamics and how we can use that to find a relationship between temperature and pressure. And the system we're going to be doing that over is we're going to imagine that we have two pockets of air. One, the initial, and then the second one being the final position, and how that expands as the altitude changes. So, we're going to need the first law of thermodynamics, which is the change in internal energy is equal to the change in heat minus the pressure times the change in volume. And so we know a few things about this situation. We know it's adiabatic, so we know that dq, which is the change in heat, has to be equal to 0. And because it's reversible, we know that the pressure has to be equal to the pressure external to the situation. And the change in internal energy can be written as CV times the change in temperature. And at an ideal gas, we know that the pressure is equal to the change in temperature over the volume. It's the specific volume. That way we don't have to deal with the moles. It's just at 1 mole. That way we don't have to deal with the N term. All right. So we're going to go ahead and start plugging these things back in. So we've got CV times the change in temperature is equal to the gas constant times the temperature over the volume times the change in volume. All right. So we're going to want to take the integral of this, but before we can do that, we want to get all the t's on one side and all the v's on the other. So we're just going to go ahead and divide that over and then take the integral. So we've got CV, which is just constant, over the integral of dt over t, and that is equal to the negative r, which is again another constant, times the integral of dv over v. All right, and so our bounds of integration here are just going to be the temperature and volume at these initial and final conditions of this pocket of air. So we've just got T initial, T final, and then we've got the V final and the V initial. All right, so let's just go ahead and take the integral. So we end up with CV times the natural log of the final temperature over the initial temperature, and that is equal to the negative r of the natural log of the final volume over the initial volume. And we don't want the natural log here, so we are going to apply some rules here. We're just going to go ahead and manipulate this so we don't have the CV and the R terms, so we're going to divide this over, and then the natural log rules let us pull that up to the top. And then we're just going to go ahead and raise it to the E power so we don't have to deal with the natural logs anymore. So, simplifying that, we get the final temperature over the initial temperature is equal to the final volume over the initial volume, all raised to the negative R over CV powers. But we don't want these in terms of volumes. We're looking for a temperature and pressure relationship. So what we know from up here, that because it's an ideal gas, we were able to find the pressure in terms of these other terms. We can also find the specific volume in terms of the other three terms. So what we've got is the volume is equal to RT over P. So let's go ahead and with this go ahead and plug this in for these conditions. So that gives us the temperature final over the temperature initial is equal to the temperature final over the pressure final times the pressure initial over the temperature initial. And this is all raised to the negative R over CV. Alright, so now we don't want the temperature on this side, we just want the temperatures on this side. So we're going to go ahead and do some algebra manipulation that will allow us to get rid of these terms. And so what we're going to end up with is, because this is to the first power, and we're going to move this and multiply by the temperature final over the temperature initial time, or raised to the positive R over CV power. And so you'll see what we end up with here. We got 1 plus R over CV is equal to the pressure initial over the, ooh, that looks too much like rho. We've got pressure final, and that's the wrong pen, to the negative R over CV. Alright, so now we notice that we can rewrite this, because we're trying to get rid of this power just so we have the relationship here just much cleaner. So we notice that this can really just be written as the CV plus R over CV, and we need to take the reciprocal of both sides. So we need to multiply by the reciprocal. So the reciprocal is going to be CV plus R, and raising this to the reciprocal power is just going to cancel it out. So then we end up with the temperature final over the temperature initial is equal to the pressure initial over the pressure final, raised to the, we've got the CV term, it's going to cancel out here, and then we've got negative R over CV plus R. And that is our relationship between temperature and pressure. So, in the next part, we are going to combine this relationship between temperature and pressure with the relationship we found in the first part, and combine them together and see what magic we can make happen. Alright, now we are on to the final part, where we are trying to find a relationship between pressure and the change in height, and the temperature and the change in height. So what we're going to do is use these two equations that I already wrote down that we solved just a few minutes ago, and we are going to go ahead and combine them. So first thing I'm going to do is I'm going to simplify this equation so that we can plug our T into this equation up here. So I'm going to go ahead and do that. Pretty easy, just multiply the initial temperature over, and you might notice that I dropped the final here, and that's just to make it easier to notice that this is the final temperature between the two. And then I'm also going to rename this value star, just so I don't have to keep writing it, just this value here, star. Alright, so let's go ahead and plug in our equation into the other equation. Alright. R, and then so we've got T initial, and then we're going to multiply, and because this is in the denominator, we're going to go ahead and flip this, so we get the pressure over the initial pressure raised to the star. Alright, so I'm going to go ahead and just start simplifying this down. We notice that this is P both on top, so we're going to want to combine that. This is a 1, and we've got star, so we want to make that equal to negative P, and then we're going to go 1 plus star times molecular weight times G, gas constant times the initial temperature, initial pressure to the star. All right, so now we want to get our pressure on the same side and our dz over to here. So we're going to multiply that over and then divide this over. So we end up with p to the negative 1 minus star dp, and that is going to be equal to negative molecular weight times r, which are initial pressure initial to the star, times dz. All right. So now we're going to go ahead and take the integral of both of these. All of these we will know in our equation, and then we are going to need some bounds, and like before, we're just going to go ahead and use the bounds of like the initial and final pressure and then positions. So we've got the initial pressure and then a final pressure, and then we've got an initial position and a final position. All right, so this will end up giving us a negative, I'm going to go ahead and do this right side first, mg over r ti, and I'm going to pull this out here and make this equal to negative here times the final position minus the initial position, and then we are going to end up with 1 over star p to the negative star. And to simplify, oh, and I almost forgot the bounds of integration here. Initial, final. All right. And so the first thing we're going to do is multiply this over. This should have a negative, sorry. Multiply this over to here, and we're going to take the reciprocal of that, and then we'll have the difference of these two here. So we've got pressure final to the negative star minus pressure initial to the negative star, and that's going to be equal to, and then the negatives will cancel, and then we'll end up with molecular weight times G over star times the temperature here, and then we've got negative star times the final position minus the initial position. All right. So now we're going to be able to move this initial pressure to the negative star over, and then we're going to be able to pull it out, factor it out. So I'm just going to do that all in one step to the negative star, and that's going to be equal to the initial pressure to the negative star times the 1, because that's still there, plus the initial, not initial, so the molecular weight times G times star over gas constant times the temperature initial times the final position minus the initial position. I need another set of parentheses. All right. So we don't want this negative star, power negative star here or here. So what we're going to do is get rid of it by its reciprocal. So we are going to end up with the final pressure is equal to the initial pressure times 1 plus, we've got to copy all this over again, to the negative 1 over star. Alright, so now we want to go ahead and plug star back in, and you see it's the negative reciprocal, so we are just going to get rid of the minus sign and then flip it. So we're going to end up with the final pressure is equal to the initial pressure times 1 plus molecular weight and gravity are going to stay the same. And then we're going to have CV plus R. The R is going to cancel. So we end up with oh no, the negatives won't cancel here, so sorry. Lost in the algebra here, and then the R's are going to cancel, and then we end up with the specific heat plus R, all that times the initial temperature, and that's multiplied by the final position minus the initial position. And then here we've got the negative, and it's the reciprocal. So here we're going to end up with CV plus R over R. And that is our final relationship between the pressure and position. Alright, so that's one of the two things we wanted. Let's zoom out here, get more space. The other thing that we wanted was how temperature relates to the position. So I'm going to go ahead and zoom in a little so we can see. So my writing's a little bit smaller. And so what we're going to want to do is plug back into this equation over here. We're going to want to plug, instead of plugging in the temperature into here, we're going to want to plug the pressure into here. So what this will let us do is, just need a little bit more space. Let me see what I'm writing here. Alright, so we want the final temperature. Well, looks like I added, no, that's right, temperature final, we want that to be equal to the initial temperature times the initial pressure over the final pressure to the star power. Alright, so we see that the final pressure here, these are the same even though this one has a PF. We want to plug that in, but we notice that this will all be on the bottom here, and that this initial pressure will cancel out, and then this will also cancel with that up there, because we've got the negative here, it'll be positive, and it will all work out. So we'll just end up with all of this in here instead of all of that. So this is just a really easy simplification. So we just end up, and we just need to copy this portion over here. So let's do that. Let me just show more clearly what I'm doing. We're adding this equation in for that, and we end up with the final equation that looks like this, times the final position minus the initial position, all that. And it's not raised to a power because the power's canceled out. And so we're going to do what we did before and just go ahead and plug back in for star. Alright, and it just ends up with what we had down here, which was the specific heat plus R times the initial temperature. Oops, didn't mean for that close parenthesis to happen. Times the final position minus the initial position. And that is our relationship between between temperature and position as we go from one pocket of air to another pocket of air. Thanks for watching.